All right, so we're going to pick up where we left off last time with writing these equilibrium expressions. Whoops. All right, so here's our balanced chemical equation. And I want everybody to give me that Kp expression for this reaction. Okay, building this Kp, I'm going to remember first what over what? Products over reactants, all right? In this case, it's a Kp. The P stands for pressure. So it's the pressure of that product HF divided by the pressure of my reactants. All right, and then we also got to remember that our coefficients are going to become exponents. All right, so I'm going to have to square that pressure of my hydrogen fluoride there. Okay. So we're going to take this now, and now we're going to set some initial conditions for our reaction here. All right, we're going to combine hydrogen and fluorine into an empty flask, each with a partial pressure of 1.5 atm. All right, and so from here, we should be able to set up one of our ice tables. All right, so I want y'all, this is what we learned last time. I want y'all to see, if you can't remember here, how we set up an ice table given this balanced chemical equation and these initial conditions here. All right, so I got my shell of my ice table here, where each column is the pressure of each gas in that balanced chemical equation. Then I have my rows, the ICE. So the I stands for initial, so that's where I'm going to plug in my initial conditions. That C is that change box, which we're going to leave as that variable. And then that equilibrium box, E, is where we sum up those first two rows. All right, so see if you can't fill this in based on what we did last class. Okay, so I got my initial conditions. The next row here, the change row. This is the important part, right? This is going to be the part that's going to be a little tricky, but once we get the routine down, it's not too bad. Okay, our change box is what we don't know. So we're always going to start by putting that unknown variable x in there. That's what we're trying to solve for. Okay, we got 2 more steps though before we're done. We got to worry about the sign of that change box, right? And remember, reactants, they get consumed in our reaction. Their concentrations go down. So x is going to have a negative sign for our reactants, but for our products, concentration goes up, so we got a positive sign. All right, and then lastly, we got to include that stoichiometric coefficient, my 2 here. All right, so that's going to appear in my change box for that product HF. All right, and then for our equilibrium box, we just sum up those 2 rows. So that would be 1.5 minus x. Oops. (1.5 minus x), and 0 plus 2x is just 2x. All right? Okay, first of all, give me a second. I realize I'm not recording. Oh, haha, JK. Okay, so previously we were introduced to this type of problem using these ice tables, and kind of we were given one other piece of information beyond just our initial conditions, which was the concentration or partial pressure of one of these at equilibrium. If we had any one of these at equilibrium, we could solve for x and fill in what the rest of them were. Okay, so that's going to be one piece of information that we could be given to complete this problem. The other piece of information, and this is what we're going to do today, is if we're told instead what the Kp for our reaction is. So what the value of that equilibrium constant is. Okay, so now I'm going to tell you that the Kp of this reaction is 73.4, and I want to know what the partial pressure of our product HF is at equilibrium. All right, so let's think this through here. How are we going to go about this? Again, if we look at our Kp expression, what piece of information are we given? We're given this part over here, right? The value on the left-hand side. So what do we do over here? Well, this is importantly, because it's our equilibrium expression, you can't just be plugging in random pressures, right? This is specifically the partial pressure of all these gases at equilibrium. All right, but if we look at our ice table, do we have the partial pressure of these gases at equilibrium? Right, the partial pressure of, for example, that hydrogen gas. If I look on my table, partial pressure of hydrogen at equilibrium, well, that's just going to be 1.5 minus x. Likewise, what's the partial pressure of fluorine at equilibrium? Again, partial pressure of fluorine at equilibrium. This box right here, that 1.5 minus x. All right, and then lastly, my partial pressure of my product at HF at equilibrium, according to my ice table, is 2x. So now what we're going to do is we're going to pick up all of this from our ice table and insert it into our equilibrium expression. All right? Let's go for it. Okay, so this is now going to be 2x, and notice that this is squared in my equilibrium expression, right? It's very important. We cannot just put a 2 over here. We got to square the whole thing. We got to square the 2 and the x, so we got to put it in parentheses, right? This is not the same thing as this, okay? Cool, so we're going to put that whole thing in parentheses, square it, and then on the bottom is that 1.5 minus x times 1.5 minus x. All right, I'm going to simplify this a little bit by scrunching these together on the bottom, because 1.5 minus x times 1.5 minus x is 1.5 minus x squared. So here we go. We get 2x squared over 1.5 minus x squared. All right, so what we really want to just kind of take note of here is that we know already what that value of k is, right? We can plug that in. That's 73.4. So that means there's only one variable in this equation right here that we don't know, that value of x, okay? Now, it's not necessarily the easiest algebra in the world, but the bottom line is if there's only that one variable, we can solve for that one variable, right? So we only have one thing that we got to look at here. We know that value of Kp. Some people like to plug in the value of Kp right now, make it 73.4. I don't love that. I would much rather leave it symbolic, and so that's what I'm going to do, but it's the exact same steps here. Okay, so again, a little bit of algebra to get there, but our goal here is to solve for x. Okay, one of the things that we're going to do here is use the fact that since we have the same exact exponent on the top and the bottom, this is the same thing as 2x over 1.5 minus x all squared. All right, and our x is stuck within that exponent there. But how can I get rid of that exponent? What can I do to both sides? Square root. And you can do anything you want as long as you do it to both sides of your equation here. Okay, so now we have the square root of Kp equals 2x over 1.5 minus x. All right. Cool. So our goal is to solve for x, but it's kind of a pain. We have it in the top and in the bottom. How are we going to get to that value of x? Well, we need to get this thing that's trapped under here out from that denominator. So how can we get it out from the denominator? What are we going to do to both sides? Multiply. That would just put the other x on the bottom, right? So what we want to do, I mean, you could probably get to it that way as well, but there's probably a million ways to do this here. However, we can definitely get it unstuck by multiplying both sides by that 1.5 minus x, right? By that whole thing that's in that denominator. That cancels it out over here. Okay, we need to get those x's together, though. I have an x on the left and an x on the right, right? We need to combine them. But first, we're going to have to distribute this Kp inside those parentheses, right? Or rather, square root of Kp. So square root of Kp times 1.5 minus the square root of Kp times x equals 2x. Okay? I think from there, I believe in y'all. All right, see if you can't solve for x here given what we've done thus far. Take it the rest of the way. Okay, again, you have an x on the left and an x on the right. You need to combine those together. That's going to be the next step. And if you think you got it, you can go ahead and plug it in using your value of Kp that we were given. Should get something around 1.2. Okay, so my next step, in order to get those x's together, they both have to be on the same side. So I'm going to add square root of kp to both sides. Square root of kpx, sorry. So square root of kp times 1.5 equals 2x plus square root of kpx. All right, and this is one of the fancier algebra moves here. We are going to take this right here and factor x out of that. This is the same thing as x times 2 plus the square root of kp. So if I have square root of kp times 1.5 equals x times 2 plus square root of kp, how do I solve for x? Yeah, divide both sides by what's in parentheses there. Okay, so we get x equals square root. Now I'll plug in, what did I say, 73.4? 73.4 times 1.5 divided by, and I'm going to put parentheses in my calculator so that I don't mess up my order of operations. Okay. We get a value of x of 1.2161, et cetera, et cetera. All right, and we're done. No, right? Okay, so there's a thing about these problems. It takes a while to set up your ICE table. You go and you do all this pain in the butt algebra. You solve for x at the end, and you're like, thank goodness I'm there, right? Always make sure to remember and go back to the problem and check what it's asking for here. The problem was specifically asking me for the partial pressure of hydrogen fluoride at equilibrium. And according to my ICE table, what is the partial pressure of hydrogen fluoride at equilibrium? 2x, right? So it's not just x, it's 2x. I could have asked you for the partial pressure of fluorine at equilibrium. You would have had to have done 1.5 minus x, right? So make sure to go back and check the problem. In this case, we want that value of 2x. Okay, so just to finish this problem here, the partial pressure of HF at equilibrium is 2x, or we're going to arbitrarily say 3 sig figs here, 2.43. All right, and what should my units be, right? I was really good, and I labeled my ICE table here. What should my units be? ATM. Cool. All right, so these ICE tables, we're going to kind of see two different types of information that is going to help us solve them. So first of all, notice that we were able to set it up based only on our initial conditions, right? That's what our ICE table is based only on those initial conditions. How do we go about solving for that unknown variable that we have here? Well, we've got two ways to do it. Either we could be given the equilibrium concentration or pressure of any one of those things up there. That would help us solve for it. Or we could be given the value of that equilibrium constant, and then we just have to plug all these expressions back in to that equilibrium expression. All right? That way is a little bit more of a pain in the butt algebra-wise, but I'm going to be honest, that's normally the way that we go about solving these things, right? Normally you have, I lied. You could be doing two things. You could be measuring the equilibrium constant of a reaction, and then you would do an experiment where you knew the initial conditions, you measured the concentration at equilibrium. We'll be doing that next week in lab, actually, okay? Or you're going to do a reaction and you go look up that value in a book somewhere, and you want to know what's going to be the results of that reaction, right? In which case you would have the value of Kp, you would plug in your initial conditions of your experiment to get an idea of what value you would get at equilibrium, right? How much product would, for example. Okay, cool. So last concept we have to introduce here is what's called the reaction quotient. All right, so just to review, K, that's what we called our equilibrium constant. All right, we get our equilibrium constant by plugging in equilibrium concentrations to our equilibrium expression. Right? Products over reactants, coefficients become exponents. If we do a reaction and we measure the values at equilibrium, we plug those in. That's the magical thing, right, about equilibrium. We always get that same constant value if we plug in equilibrium concentrations into our equilibrium constant expression. All right? So then what is Q, our reaction quotient? This is when we plug in values that are non-equilibrium. Plug in non-equilibrium concentrations. Into that exact same equilibrium expression. All right, so if we have equilibrium values and we plug them in, we always get the same number, and we call that the equilibrium constant. We can take that same equilibrium expression, this thing, whoop, not that thing, this thing up here, and plug in any other values, right? And then we wouldn't call it K, we would call it Q. Okay? It's the exact same expression, exact same products over reactants, coefficients become exponents, exclude solids and liquids. All that business is the exact same. We're just plugging in any random value we want. Okay? So why would we do that? Because we can compare the value of Q and the value of K, and it tells us something about which direction is going to be favored under those conditions. Right? And remember, what do I mean by which direction? We had to update our way of thinking about chemical reactions. We previously always thought of reactant being converted to product, what we call the forward direction, but also the product can be converted back into reactant, right? And so we could set up conditions. We want to know under those conditions, is reactant going to be converted to product, or do I have too much product? And it's actually going to go the other direction, in the reverse direction, in order to reach equilibrium. So by comparing the values of Q and K, we can say something about which direction the reaction is going to go in order to get back to equilibrium. All right, so let's think about this. Q, just like K, because again, it's the exact same expression, has that basic format of concentration of products over concentration of reactants. All right, so then let's think. Let's say that we calculated a value of Q that was greater than K. All right, if Q is greater than K, let's look carefully at our expression here. What does that mean? The numerator's too big or the denominator's too big? Right? Do I have too many products in this mixture or do I have too many reactants? Too many products, right? If Q is greater than K, that means that this numerator right here is too big. So now I have too many products. And this is a reaction that will proceed to equilibrium in the reverse direction. All right, well, by that same logic, what's going to happen if we calculate a value of Q and it's less than that equilibrium constant K? Do we have too many products or too many reactants in that mixture? Now we have too many reactants. So this is going to proceed to equilibrium in the forward direction. All right, so we can calculate that value of Q by plugging in conditions into our same old equilibrium expression. We can compare that to our equilibrium constant, and it tells us something about which direction the reaction is going to go in order to reach equilibrium. All right, so let's do an example here. Let's take our same reaction. We already got our expression built here. All right, I'm going to get rid of these little markings here. Oops. Cool. And we said that that Kp, once we plug in these values that are at equilibrium, we knew that took on a certain value of 73.4. All right, that was given to us in our problem. All right, so now we're going to look, let's say, if 0.2 atm of hydrogen, 0.6 atm of fluorine, and 3.5 atm of hydrogen fluoride are combined, which direction will this reaction go in order to reach equilibrium? All right, so we can't plug these into RK because that's reserved for pressures at equilibrium. But we're going to take this exact same expression. We're going to call it Q, and now we can plug in whatever the heck we want. All right, so take a second, plug in our conditions here, and tell me whether this reaction is going to proceed in the forward or the reverse direction. right, so we're just going to plug in for each of these here. My hydrogen, my fluorine, my HF. All right, and we get a value of 102. Okay, so what would we say? Is this going to go in the forward or the reverse direction here? This is going to, so we have a value of Q that is greater than K, right? So that's when we said we have too many products. So actually this HF is going to decrease, pressure is going to decrease as product gets converted back into reactant in order to reach equilibrium. All right, so this new value, Q, our reaction quotient, we can compare that to our equilibrium constant K, and that tells us which direction our reaction is going to go in order to reach equilibrium. Okay, this is a sort of quantitative understanding of what was first a qualitative observation known as Le Chatelier's principle. There may or may not be another E between the T and the L. I'm not confident about that, but this is close enough, all right? All right, so Le Chatelier's principle was this observation that basically said if a reaction is at equilibrium, and then you go in there and you increase the concentration of reactant, all right, so let's think about this based on what we just discussed with Q here. Let's say that our reaction is at equilibrium, and then all of a sudden I add a whole bunch more reactant here. What's that going to do to the value of Q relative to K if I make this denominator really big? It's going to be smaller, right? So if we add a bunch of reactant, that's going to shift this reaction in favor of the forward direction, right? It's going to have to get back to equilibrium by proceeding in that forward direction. So we're going to say it shifts forward. All right, and we can certainly think about it by looking at that expression for Q and convincing ourselves, does this make Q bigger or littler? But math isn't exactly everybody's favorite thing in the entire world. Some people aren't super comfortable with that. So there's kind of another qualitative way that we can think about this here, which is, let's take a very simple reaction here. A being converted to B, right? Reactant being converted to product. Okay, and we're going to imagine that they're on this little teeter-totter here, and that at equilibrium, concentrations aren't changing, they're all perfectly balanced. Okay? But what happens if I go in and increase the amount of A? I put a whole bunch more A on this side of my little teeter-totter. What's that going to do to it? All of a sudden, boop, A is going to be on the ground, and B is going to be up here in the air. All right, so that's what happens if I increase A. Well, if this thing wants to get back to equilibrium, if it wants to get back to being balanced here, what's going to happen? Am I going to have to move stuff from my reactant side to my product side, or from my product side to my reactant side? What's going to restore order here? I got to take stuff from this side and move it over here, right? So in order to get back to equilibrium, I have to convert A to B, or another way of saying that, convert reactant to product. All right, so let's think of two other ones that I want you to fill out here. You can use either the look at Q equation method or the teeter-totter method, but what's going to happen if we increase our product concentration or if we decrease our reactant concentration? All right, which direction is that going to shift this reaction, forward or reverse? So see if you can apply either of the two logics that we laid out to answer these here. All right, so if I increase B, now all of a sudden it's the product side of my teeter-totter that's on the ground. And the only way that I can get this back to being stable again, back to being equal again, is if I convert product to reactant. If I move stuff from the B side over here, right? So this would have the effect of shifting the reaction in the reverse direction. Okay, what about if I decrease A? Cool, so if I do that, all of a sudden we got the exact same thing. Now all of a sudden the product side is too heavy, right? So now that side's on the ground, so I have to again pick stuff up over from the product side and move it to my reactant side, what we would call shifting in the reverse direction. Okay, and then there's one other possibility. We could actually take product out of the mixture as it's being formed. We could decrease our product concentration. Right, and that would shift things. So now I have too many reactants, or A is on the ground here, and in order to reach equilibrium, it would have to shift in that forward direction. Okay, so this was Le Chatelier's principle. If a reaction is at equilibrium and all of a sudden you change those conditions, you throw it out of equilibrium, right? Which way is it going to go in order to restore its equilibrium? Because again, all reactions proceed towards equilibrium. All right. Le Chatelier's principle, we use all the time to increase reaction yield. Right? We use these two shift forward methods all the time in order to increase the yield of a chemical reaction. All right, so what do I mean by that? Okay, let's take a look at a very simple reaction that you would do in organic chemistry. It's called a hydration reaction, where you take water and you mix it with this organic compound. And it forms this, what's called an alcohol. Oh, nope, sorry, C4, not C6. All right, we're going to take this back to the same sort of graph that we were looking at the very beginning of this chapter, and actually of the whole semester, our kinetics chapter as well, where we're going to make a plot of concentration versus time. Okay, and I'm going to keep track of all of these various compounds here using these different colors. Okay, so I'll keep track of water in blue, the C2H4 in red, and this ethanol, this product here in orange. Okay, this is all 1 to 1 to 1 here. So if I start out with an equal amount of water and my alkene, my organic compound here, the C2H4, I'm going to put those both starting at the same place. All right, and we don't have any product at first here. What's going to happen to my concentration of my reactants? It's going to decrease. What's going to happen to the concentration of my product? It's going to increase. Okay. The organic compound is also going to decrease at the same rate as water. So I'm going to use this kind of like little checkered line to show that it follows the same pathway here. They're kind of right on top of each other. Boom. All right, but we can see that when equilibrium is reached, I haven't consumed all of my reactant yet, all of my organic compound, and I haven't gotten quite as much product as I would like to, right? My theoretical yield for this reaction would be all the way up here. Since it's 1 to 1, I know that it can get to that same height where my two reactants started. Okay? And again, our whole goal is to, there's many different branches of chemistry research, one of which called synthesis, where you're trying to make crap. I mean, that's the name of the game, right? So you want as much yield as possible. You're not trying to go through a whole bunch of work and then get 5% yield or something like that. Okay? So what can we do here to maximize our yield? Where one of these two reactants is way more expensive than the other one, right? This one right here is the one that we got to buy and store special and all that stuff. Well, water, that comes straight from the tap, right? So instead, what we would do when we carried out this reaction is we're going to increase the amount of water. So let's say right now, all of a sudden, I'm going to increase the amount of water that is in that reaction mixture. Okay, let's just make note. We add H2O. Well, according to Le Chatelier's principle, what's going to happen when I increase the concentration of one of these reactants? Is it going to shift the reaction in the forward or the reverse direction? In the forward direction. So now all of a sudden I'm going to have more reactant being converted to product. So now all of a sudden my water and my C2H4 are going to start to decrease again. And my product concentration is going to start to increase. And now I'm that much closer to my theoretical yield for this experiment. I almost got the maximum amount possible, almost consumed all of that C2H4, right? I could add even more water and then get even closer to that 100% yield, right? The bottom line is we can use Le Chatelier's principle to maximize our yield. I mean, it costs money to run a lab, right? So you look at your two reactants and you're like, all right, which one's the more easily available? Which one's the easier to get rid of in my reaction mixture? There's a few different considerations, but you just crank up the concentration of that one reactant, and that helps push that reaction towards 100% yield. What's up?
How does that like coincide with what we've learned about limiting reagents in our reactants?
So that's specifically for like in a mechanism the slowest step, right? So it's not like it's limiting in how much can be consumed. It just means that you're going to be limited in the rate of your reaction. So that would correspond to how steep these curves are on this graph, right? Does it take a long time to get to equilibrium, so it's this really shallow curve that takes forever, or does it just jump up there real quick? That would be the rate of our reaction, would be how fast, right? The slope of this curve here is what the kinetics of it is. Now we're looking at like actual amounts that we get at equilibrium and stuff.
Right. I'm referring more to like the limiting reactant stuff we learned in like Chem1A, where it's like the
Oh, limiting reactants. So the bottom line is in Chem1A, you always pretended like reactions gave you 100% yield.
Yeah,
So you were always only looking at this value here.
Okay.
Right? And that would depend on, yes, we started out with the same amount of blue and red and stuff like that. I am going to be limited in what my theoretical yield is based on whichever one of those is my limiting reactant. But the idea is we want to convert 100% of that limiting reactant.
Right. Okay.
All right? And that's the name of the game, is whichever one's limiting, in this case it's going to be the red one. Right? We don't want to use too much of that. That's the expensive one, whatever. So that's going to be limiting. That's going to tell us what our theoretical yield is. But we want to get as close to that theoretical yield as possible. And we can just crank up exactly. And we can crank up the other one, and that gets us that much closer, right? So if in equilibrium, some equilibriums favor the products very strongly. But some of them, you get this pretty even distribution at equilibrium. And that's when you want to take advantage of Le Chatelier's principle to really crank up your yield. Cool. All right, so that does it for our equilibrium chapter here.